Thank you, Michael, for your introduction. Hi everyone. My name is Zephyr. I'm a second-year PhD student from UC Irvine. So today I'm going to talk about our work on Milkomeda, which safeguards mobile GPU interface using WebGL security checks. So let's quick go over what mobile GL looks like. The GPUs are commonly used by mobile apps. Right? Look at this Minecraft, the racing game, and they all heavily use GPU for graphic rendering. So this is how the graphics stack in mobile OS works. We have this, in kernel mode, we have this GPU device driver, and in user mode, there's an application. And this application, the app code that want to do 3D graphic rendering will call the APIs in OpenGL ES library. And the library will communicate with the device driver in kernel mode. But unfortunately, the GPU device driver is full of vulnerabilities. I want to show you some data. And this is the stats collected by Google researchers. It shows the kernel bugs between 2014 and 2016. And these are the bugs reachable by unprivileged apps. As you can see, the red part, 27% are in GPU device driver. So these are just bugs, right? Not necessary security vulnerabilities. So we take a look at the security vulnerabilities. We find this 64 vulnerabilities in the National Vulnerability Database. And on the y-axis, you have the number, and the x-axis shows the year. We have two observations. First, these vulnerabilities are very new, very recent. Mostly are in 2016 and 2017. And second observation is that these vulnerabilities are always high severity. Yeah, you might think this kernel vulnerability are very hard to exploit, but that's not the case, right? So there are hundreds of OpenGL ES APIs, and all these, many of these API have memory pointer, and they are highly stateful. So there are a lot of attacks on this interface. And because how the system work, how the mobile graphics work, app code doesn't have the malicious app code don't have to go through the OpenGL ES library to communicate with the driver. It can directly, just from the app code, it can directly communicate with the driver and exploit the bugs. So we look at some of the bug reports, and I make some POC. I can build into an Android app. If I click the app, the kernel crash, right? So it's very easily exploitable. So in Milkomeda, we assume the GPU device driver is trusted, but full of vulnerabilities, buggy. We want to protect the driver against malicious app code. So actually, the web browser people are already trying to address this problem, and they come up with a solution. So let's see if we can reuse that, right? So I want to quickly go over what is WebGL. So basically, WebGL is a wrapper for GLES APIs for JavaScript. So it was introduced in 2011, and over the years, it has grown very fast and become very popular. And our study shows at least 53% of the top 100 websites are using WebGL. Right? Apple uses it for a product page, and Google Map uses it, NASA uses it, NIST has a data virtualization using WebGL. Right? So actually, the browser concerned with WebGL security because they share exactly the same attack model. So the web app code that want to use GPU for hardware acceleration will have to use this OpenGL ES library. And if we want to give access to this web app process, we must have the process must have the access to GPU directly. So exactly the same attack model. Indeed, so Microsoft when WebGL first come up, Microsoft had this blog post saying WebGL considered harmful, and thus they cannot endorse it. So the main reason is because WebGL WebGL relies on a third-party device driver manufacturer for the safety. So Microsoft have no control over that. Yeah, that's the reason. but eventually functionality wins. So now almost every browser supports WebGL, right? They did a lot of work and invest a lot of time on mitigating the problems. And here's the first thing they did, right? They call this direct link. Now the web app process does not have direct access to GPU device driver, but instead they have a proxy called GPU process running in backend. And this GPU process have access to GPU device driver. It has a GLES library. And for the web app code that want to use GPU, it will first call the WebGL frontend, and the frontend will send the command and data over IPC to the GPU process, and the GPU process will then execute the call. So that's not the full story, right? So remember, we mentioned that OpenGL has a lot of APIs and many attacks against this library. So they added a lot of security checks before doing the call on OpenGL ES API. So let's take a look on what these checks are. First, they check on numeric values. For example, geotext image 2D, they don't allow a negative dimension to be passed. They also have checks on deprecated values. So they check on the correctness of API calls. So OpenGL is highly stateful. So you can only call a subset of the APIs at a certain rendering stage. And for example, if a buffer is not yet generated, you cannot bind it. They have checks on shader code. So basic shader code is the code that's been compiled and run on GPU hardware. So maybe you can spot, can you figure out like what's wrong with this shader code? Yeah, it's actually the E, right? It's non-ASCII character. So there is actually a real bug report in Chromium. So this shader code will crash the browser. They have checks on the shader code. Remember that there's an OpenGL API that directly passes a binary for the GPU to execute, and WebGL blocks that. So all the shader code must go through the checks. Right? So they also have platform workaround. There are some bugs on specific device or specific version of device driver. So they just work around, disable some feature. Like this one on Arduino driver, there's a certain type of loops in WebGL shader will crash the compiler. It just disabled that. So web app is one click from user, but is that the same for mobile apps? So mobile apps, we see a lot of malicious application in Google Play Store, and there's third-party store as well. And also user can just install APK from an untrusted source. So I'm sure you heard Instant App. So this is a new feature in Android. On the first screenshot, there's this is actually a search result from Google. If you click on the link, it will install and launch this app without asking for user permission. So basically now web app is just one click away from user. It's similar to web app. So we believe they share the same attack threat model. So let's quickly go over the options we have to adopt this design. So we want to reuse WebGL security checks, right? The first thing we can do, very intuitive, we can just adopt this multi-process model. We call this direct link. We have this proxy called GPU process, and the GPU process have security checks. Yeah, of course it will work, right? But we face the first challenge. It will have significant performance drop. And to show you the performance drop, we actually implement a set of IPC version of OpenGL ES call. And on the y-axis, you have the time measured in microsecond. On the x-axis is different micro benchmarks, right? We compare between mobile app and multi-process version of OpenGL ES call. Yeah, you can visualize the performance drop is quite bad. So we don't want this overhead, but we still want these security checks. Come up with a crazy design. We want to put this security checks in the process, right? this will not work because first, app code can just jump because it's in the same address space. App code can just jump, skip the checks, or the app code can load another OpenGL ES library that does not have the check. Or even worse, the app code can just directly communicate with the driver to exploit the bugs, right? So to solve this problem, I'm going to introduce the in-process shared space. So the in-process shared space, the key idea is to have this trusted execution environment, which is the light green box. So we put all the graphic code in this memory, and this memory is only accessible from the thread that executing shared mode. So the GPU access is not allowed for the thread that's not running in the shield. So let's take a look on the flow of execution. Right? The thread running outside the shield does not have access to GPU device driver and shared memory. It wants to do some GL call. It wants to render something. It will become a shared call. So shared call is basically a syscall that returns to a designated address in the shield. So at this address, we have a call gate function that checks which API it is calling. And we go through the corresponding security checks. And then it calls the OpenGL ES library and it returns. And now the thread execute and continue to continue to execute outside the shield. Right. So let me excuse me. Let me show you how we separate the virtual address space. So both page tables are for the same process. Yeah, on the right side is before we enter the shield. On the left side is after we enter the shield. Right? They're basically the same, except for the light yellow region on the bottom. So in the shield, for the thread in the shield, this region is accessible. For the thread outside the shield, this region is inaccessible. So that is the memory we use to load all the graphic libraries. Right. To enforce this, we modify one first level page table entry, and the second level and the third level remain the same. So this is very efficient design because we only need to sync the page tables if there's an update to the first level page table, right? So which is very rare. So I want to show you how we port these WebGL security checks. Remember, we have this GPU process in browser. So take Chromium for example, right? We have this on the top of the GPU process. There's a deserializer IPC interface, and it for the API call, it will go to the buckle security checks, and then it will call the GLES library. For the non-sensitive API, it can just directly go through and call the GLES APIs. So we are managed to build all these security checks into a library. That's easy. And then we can have this library linked to this process, right? But the problem now we have is how we can call these security checks from unmodified app code. We don't want to modify the application code. And this interface is not compliant with the GLES standard. So let's take a closer look on the IPC interface. This is the code format of the code for each GL function on the IPC interface. So for each OpenGL ES API, there is a deserializer function that takes the IPC data, deserialize it, performs some simple checks, such as numeric checks, and then it will call further checks in the bulk of security checks. Right? So we made a Python script that automatically extracts the deserializer interface for each OpenGL ES API. And we automatically repurpose this interface. We generate this header, we generate based on the GLES specification, and we keep the simple checks. There's a numeric check, something we don't want to lose. We redirect the further call into the function in the library we have just built, and we remove the deserializer part. So now the Milkomeda interface looks like this. So app code want to do any GLES call, it would just use a standard OpenGLES interface and will call to the generated API interface. And it will then call into this bulk of security checks we build as a library. And then it will execute on the GLES library. And that is all the thing we put in the shield, right? So we managed to put everything as a tool called checkgen. So if there's an update to the browser, if they have a new WebGL security check, so we can easily port it to Milkomeda because we have this automized tool. Right now, here is the evaluation section of this talk. Remember, we have this graph, 64 vulnerabilities in GPU device driver, and we find enough information of 45 of them for further analysis, and we find Milkomeda prevent all of them. So we test Milkomeda's performance using these benchmarks. On the left side is some simple benchmark. On the right side is the benchmark that very demanding. It stress has a GPU. For example, this one have 64,000 cubes, and each of them have texture. They're rotating. So we test all the benchmarks on LG Nexus 5X. Here's the result. Right? So on the y-axis, you have the frame rate measuring frame per second. On the x-axis are the different benchmarks. So compare between normal app and Milkomeda. For the benchmark that achieve high frame rate, we also achieve high frame rate. So note that the system will cap the frame rate at 60 frames per second. That's the display refresh rate. And for the one that stress test the GPU, we achieve slightly lower but similar performance. This doesn't come at no cost, of course. So Milkomeda incurs some CPU overhead. So on the y-axis, there is a CPU utilization. We compare the normal app and Milkomeda on the same benchmark. Yeah, as you can see, we incur modest CPU utilization. So that means if there's nothing running backend, the performance will be good. But if there's some CPU demanding app running backend, there will probably be a performance drop. So remember, we have these micro benchmarks. We compared normal app and IPC version of OpenGLES calls. Now we add Milkomeda for comparison. Right? On the y-axis is time measuring microsecond. We compare the same set of micro benchmark. So as you can see, we are much better than IPC, but we are worse than the baseline normal app. So in summary, GPU device driver are full of vulnerabilities, as we all see. Right? WebGL provides security checks to check on the use of graphic APIs, and we Milkomeda repurpose these checks for mobile GL. And Milkomeda achieve high performance at a modest CPU utilization rate using this novel shield design. By the way, Milkomeda will be open source soon. And thank you. I'm open for questions.
Thank you. Siwan from Dankook University. Have you measured the TLB flush count, or have you ever explicit TLB flush after the address space changes?
Yeah, thank you for the question. So TLB, we do have a TLB flush on axis the shield. So the performance on this benchmark includes this overhead, has this overhead.
So have you measured the number of flushes?
Number of flushes. We don't have a benchmark on that, but this result includes the TLB flush overhead.
Okay, thanks.
Thanks.
Hi, Wei Zhang from Wayne State University. So nice work. And maybe I missed that. So when you the question is, how do you ensure that the sensitive calls always go through the shared process? And what if the program just directly call the drive?
Yeah, that's a good question. I think there are two parts. First, so every GL call now is a shared call. It have to go to the designated call gate and it goes through the checks. So this control flow in the shield is controlled. And the second part, I think you're asking, what if the app just called the GPU? So as I mentioned, now with Milkomeda, we have these simple checks on the driver that no GPU access is allowed unless the thread is running in shield mode. Yeah, thank you.
Hi, Ming Wei from Intel Labs. So nice work. So I just have a question about the your design about this in-process like sandbox design. So first, I wonder what exactly is the do you copy data from the outside of the application to your inner sandbox?
No, we don't copy data.
So if you don't copy, then what if there is a time to check to time to use problem?
Yeah, that's actually a very good question, and I have back a slide for that. Right. So WebGL security attacks actually have a similar attack model, and they prevent tactile attack by copying sensitive data onto the GPU process. So we basically port everything from WebGL, including these checks. That will prevent this problem.
So I'm not sure I'm quite follow. So, but still, you're not using the full GPU process, right? The data remains in that process address space, and you basically redirect control flows goes to this security check within the sandbox, and you do the checks, right? But the data to be checked is still outside of, is still in a address space where accessible by the potentially malicious app. Right.
Yes. So yeah, I think that's a good point. But actually, so we port these checks, and this check includes the copy for sensitive data.
Sensitive data.
Yeah.
Okay,
so non-sensitive data is possible to modify after.
Okay. Thanks. Yeah.
Thanks.
Hi, great talk, Moshe Kravchik from Ben Gurion. Quick question: your defense model. You mentioned you don't want to change the applications, but to implement your shield, you clearly need to change a lot of things at the kernel level.
Yep. Yeah.
So, what was your vision?
Yeah, that's a good question. So we need to have a kernel patch first, and second, we need to modify the system app launcher to include setup for the shield. So this probably will require a system update. And if someone wants to adopt our solution, I would say it's not that hard, but definitely requires some system update.
So you need to add more system calls, and you need to do these page table tricks.
Yeah,
it's kernel patches.
It's a kernel update. Yeah. Thanks.
Okay, let's then thank the speaker again.